Hello, this is Nicholas, and from the last two videos where I derived the formulas for the real valued and complex valued Fourier series, I figured an example of using these formulas would actually be in order. So let's derive the Fourier series for e to the x on negative pi to pi. So e to the x for an x being between negative pi and pi, and we'll see about the endpoints of this later on. So remember our formulas here. We had a naught being 1 over 2 pi times the integral from negative pi to pi of f of x dx. We had an being 1 over pi times the integral from negative pi to pi of f of x times the cosine of nx dx. And we had bn being 1 over pi times the integral from negative pi to pi of f of x times the sine of nx dx. And those are going to be our three building blocks for the Fourier series, along with the fact that f of x is a naught plus sigma n equals 1 to infinity of an cosine of nx plus bn sine of nx. And all this we derived in the previous video, so I'm not going to go over it. Now I'm going to actually use it. So first we're going to find what a naught is. A naught is 1 over 2 pi times the integral from negative pi to pi of f of x, which is e to the x dx. And when we integrate, this becomes e to the pi minus e to the minus pi over 2 pi. For an, we get 1 over pi times the integral from negative pi to pi of e to the x times the cosine of nx dx. So I think that's going to require some integration by parts. So let's do that. We have, that's a bad I. I'm going to differentiate e to the x. So we have alternating plus and minus signs. I think I only need 3. So we differentiate, we get e to the x, e to the x. Integrate cosine of nx. We get 1 over n times the sine of nx. And then we get negative 1 over n squared times the cosine of nx. So this integral becomes 1 over pi n. So we're basically going along these two columns, which gives us an answer, and then this column, which is another integral. So we get 1 over pi n e to the x times the sine of nx plus 1 over pi n squared times e to the x times the cosine of nx minus the integral 1 over pi times the integral. I guess you can make it 1 over pi n squared, since n is a constant with respect to x. E to the x times the cosine of nx dx. And just to, wrong thing, I got to move it over just a little, because remember that all of this right here now by integration by parts is 1 over pi integral negative pi to pi of e to the x times the cosine of nx dx. So now it just comes down to simplifying it. So I'm going to add this integral to that one, and I'm going to have a common denominator here. So I need to make this n squared over pi n squared. So then now I get n squared plus 1 over pi n squared times the integral from negative pi to pi of e to the x times the cosine of nx dx. That's equal to, again, yeah, I'll leave it like that for now. 1 over pi n e to the x times the sine of nx plus 1 over pi n squared e to the x times the cosine of nx. Okay, and so then we can just divide by this n squared plus 1 over pi n squared, and we're going to get that the integral from negative pi to pi of e to the x times the cosine of nx is equal to When we take 1 over pi and we divide by n squared plus 1 over pi n squared, that's the same thing as multiplying by the reciprocal pi n squared over n squared plus 1. A pi and an n will cancel with a pi and an n. And so we're going to get n over n squared plus 1 e to, I'll write like this, times e to the x sine. No, I don't need to write it like that. E to the x, because it's all being multiplied. E to the x times the sine of nx. And then when I divide 1 over n squared by n squared plus 1, that's the same thing as multiplying by the reciprocal, pi n squared over n squared plus 1. And that will cancel out. So we get plus 1 over n squared plus 1 e to the x times the cosine of nx. Notice that this is actually like the coefficients are actually just given by like the Pythagorean theorem, or like the coefficients in front of our cosine. So, right, like we had a cosine of nx and we just had a sine of 1x. And so that gives us a like magnitude, like using the squaring, like the coefficients. We'd square the n, and we'd square the 1, and that's where those coefficients come from. It's a general, you can find it on any standard table of integrals. I just wanted to show it out in completeness. So now, see if I have this one actually. Oh, and all of this is still, so all of this here is equal to our an. But again, remember that this was a definite integral from negative pi to pi. So we still have to actually evaluate this here. So when we let x equal pi and negative pi in this first one here, we're going to get that, well, first of all, sine of pi is 0, sine of negative pi is 0. So in all, this whole term here cancels out, which is nice. And then when we let cosine be pi, we get what? Cosine of pi is, oh gosh, cosine of pi is 0. Oh, okay, I see. I'm sorry, I blanked out there. See, okay, in the first one here, when we had sine of nx, we let x be equal to pi, so we had sine of n pi. Sine of n pi is always 0 for integer n. And when we let x be equal to pi and negative pi, we get cosine of n pi. So cosine of n pi, depending upon what n is, that's going to be 1 or negative 1. Right, if n is equal to 1, we get cosine of pi, which is going to give us a negative, negative 1. And when we let n equals 2, we get cosine of 2 pi, which is 1. So in general, cosine of n pi is just given by negative 1 to the n. And then cosine of negative n pi is, right, if I had cosine of negative n pi, cosine of negative n pi is the same thing as cosine of n pi, since cosine is an even function. And so we would again get our negative 1 to the n. So what we would get is, we would have also here, notice that we have an x here, so we have to plug in e to the pi minus e to the minus pi. So we would have, we would have e to the pi minus e to the minus pi times our negative 1 to the n over n squared plus 1, and that's going to be equal to an. And I don't think I have messed that one up. Okay. Now it turns out, so we're going to find Bn. I'm not going to show all of the steps for the integration by parts, because if you're learning a Fourier series, integration by parts should be already known to you. So I'm just going to say that b sub n is given by the integral from negative pi to pi of, that's e to the x times sine of nx dx. And that integral, similarly, right, turns out to be, well, we'd have a 1 over pi out front, and then the integral of this e to the x sine of nx, using what, like a table of integrals or whatever it is you'd like to use, you're going to get e to the x over 1 plus n squared times cosine of nx minus, you're going to get sine of nx minus n cosine of nx. And you can look that up in a table of integrals or whatever you'd like, and we're going to be evaluating that from negative pi to pi. And so what that turns out to be is that we would get 1 over pi times 1 plus n squared, right? Times our, I'll write it like this, e to the pi minus we'll put it like this, e to the pi times minus n times negative 1 to the n minus e to the minus pi, the negative signs are just waiting to bite me, times negative 1 to the negative n. And I think that's all the parentheses I need there. So that's our b to the n, or that's our b sub n right there. So now what this tells us is that the Fourier series for e to the x is e to the pi minus e to the minus pi over 2 pi. That's the a naught component that we found at the very beginning right here. Plus sigma n equals 1 to infinity of, okay, ready? So we have negative 1 to the n times e to the pi minus e to the minus pi over pi times 1 plus n squared cosine of nx. And so that is just the a sub n that we found a while ago. I forgot to multiply by the 1 over pi right here because we had in the beginning, a 1 over pi out front here. So that was our a sub n we found at the beginning. And then our b sub n is plus, okay, yeah, I added the cosine of nx. So plus, now we're going to have plus negative n times negative 1 to the n times e to the pi minus e to the minus pi over pi times 1 plus n squared times now the sine of nx. And that's the Fourier series for e to the x. So now you're thinking, oh my gosh, why would I ever do that? That's for another video. One thing I would like to point out is you get kind of a cool sum here if you let x equal 0. So something I would like to point out, if you let x equal 0, you get e to the 0, which is 1. So you get 1 equals e to the pi minus e to the minus pi all over 2 pi. Plus sigma n equals 1 to infinity of, now watch this, so the cosine of nx, when we let x equals 0, we get cosine of 0, which is 1, so that's nice. This thing just becomes a 1. And then when we let x equals 0, sine of nx goes to 0, and so this whole second part here goes away. So what we really get is 1 is equal to all of this, plus sigma n equals 1 to infinity of negative 1 to the n, e to the pi minus e to the minus pi over pi times 1 plus n squared, which that means that 1 is equal to e to the pi minus e to the minus pi over 2 pi. And then what I'm going to do is I'm going to take this here, since these are all just constants in red, and bring it out front of the sum. So plus e to the pi minus e to the minus pi over pi times the sum n equals 1 to infinity of negative 1 to the n over 1 plus n squared. From here, we can actually solve for what the value of this sum is, which is a pretty cool sum. And so what am I going to want to do here? I guess I'll make this a 2 pi. So 2 pi over 2 pi. So 2 pi plus e to the minus pi minus e to the pi over 2 pi is equal to e to the pi minus e to the minus pi over pi, sigma n equals 1 to infinity of negative 1 to the n over 1 plus n squared. And then now what I can do is multiply by the reciprocal of this. So pi over e to the pi minus e to the minus pi times, now I'll write it like this. I'll write it as e to the minus pi and e to the minus pi minus e to the pi over 2 pi plus 1 is sigma n equals 1 to infinity of negative 1 to the n over 1 plus n squared. The pi and the pi will cancel out. Okay, yeah. So, and then also notice that we can't do much here with it looks like we can, but we really can't with this part right here, because we have a e to the, we could write this as the negative of negative e, or e to the negative pi minus e to the pi. We could do that. That would cancel out with that, leaving just a negative 1/2 plus a 1, or in other words, a 1/2, is equal to this sum right here. And that is a pretty cool result, I would say. I think with that, I have done a good example with the Fourier series for e to the x. And the Fourier series can be used to evaluate some pretty tricky sums. Like this right here, finding the exact value would probably be a little difficult. So in the next video, I'm going to derive the Fourier series using the complex version for e to the x, and I'm going to look at that sum that results when we let x equal 0, and it's going to be like kind of crazy, and I'm going to ask you, well, what did I do wrong? Because the result is just really, really strange. Anyway, I